sklearncovariance Description: the shrunk covariance estimator in scikit-learn provides a regularized version of the sample covariance matrix. It addresses the issue of singularity and instability in the covariance matrix, especially when dealing with high-dimensional datasets or cases with fewer samples than features. By introducing a shrinkage parameter, it blends the sample covariance matrix with a scaled identity matrix, resulting in a more robust and stable estimate. Inputs: X a 2D array representing the data. Each row corresponds to a sample, and each column represents a feature. Shrinkage: the shrinkage parameter, which controls the degree of regularization. It can be a float value between 0 and 1. A higher shrinkage value leads to greater regularization. Outputs: covariance: the estimated shrunk covariance matrix, which is a square matrix with dimensions equal to the number of features. Location: the estimated location mean of the data, which is a 1D array with length equal to the number of features. Steps: calculate the sample covariance matrix from the input data X. Compute the shrinkage parameter based on the provided value or using the Leduit-Wolf shrinkage estimator if shrinkage is set to auto. Shrink the sample covariance matrix by combining it with a scaled identity matrix using the shrinkage parameter matrix. Frobenius norm of the difference between the shrunk covariance matrix and the sample covariance matrix. Log likelihood of the data under the estimated shrunk covariance matrix. Visualization plots. Heat map of the shrunk covariance matrix to visualize the correlation structure between features. Scatter plots of pairs of features, highlighting the distribution of data points and the impact of the shrinkage on the estimated covariance. Fine-tune parameters. Shrinkage: adjust the shrinkage parameter to control the degree of regularization. A higher value introduces more shrinkage and stabilizes the covariance matrix but can also lead to bias. Assume centered if set to true. The input data is assumed to be centered, which can improve efficiency. Uncertainty methods. Bootstrap resampling: generate multiple bootstrap samples of the data and estimate the covariance matrix for each sample. This provides a measure of uncertainty in the estimated covariance. Bayesian estimation: use Bayesian methods to estimate the covariance matrix, incorporating prior information about the distribution of covariance matrices. Challenges and fixes. Challenge 1: in cases with high dimensionality or limited data, the sample covariance matrix can be singular or nearly singular, leading to unstable estimates. Sample use case: a dataset with 100 features and only 50 samples. Fixes to challenge 1: apply shrinkage to regularize the covariance matrix and mitigate the effects of singularity. Challenge 2: the sample covariance matrix can be sensitive to outliers or non-Gaussian data, leading to biased estimates. Sample use case: a dataset with a few outlier samples that significantly influence the sample covariance. Fixes to challenge 2: utilize robust estimation methods or outlier detection techniques to mitigate the influence of outliers before calculating the covariance matrix.